All right, we are back. Sorry about the lengthy videos today. I just wanted to make sure you had a good example of a 2x2 and a good example of a 3x3. For this 3x3, we are just going to find the general solution, not an initial value problem here. So let's go ahead and start by writing this in matrix form. All right. So this is my y prime equals a times y. We are going to, remember, find our eigenvalues by finding the determinant of a minus the lambda identity matrix. So we're subtracting those lambdas on the main diagonal. And everything else will stay the same. Which is a pretty boring matrix, but probably will be good for us in the long run, because now to find the determinant, we're going to have a little bit of work here. So we have that 2 minus lambda that we're starting with. It's being multiplied by the 2 by 2. Think of your cross product the way we did those. So I'm going to go ahead and multiply that out. And then we get minus a positive 1 right here. So that would be a lambda squared minus 4 lambda plus 3, it looks like. And then we always change the sign of the middle element here. So we get plus 1, and we go ahead and do that 2 by 2. So I'm going to go ahead and just, when I take negative 1 times 2 minus lambda, I'm just going to distribute that right away. And then it looks like I have another minus positive 1. So here it looks like we get lambda minus 3 when we simplify. All right, last one with the 2 by 2. So just multiplying right away, we get 1. And then if I distribute this, I would get a negative 2 plus lambda. But remember, I have to subtract that. So it looks like I'm taking a positive 2 minus lambda there. So I would get a positive 3 minus lambda. So I'm going to go ahead and just do the rest of my multiplication here, distributing the 2 to everything, distributing the negative lambda to everything. Okay. So getting this into standard form here, negative lambda cubed. And then it looks like I have a 2 lambda squared and a 4 lambda squared. So a 6 lambda squared. I have a negative 8 lambda, a negative 3 lambda, plus a lambda, plus a lambda. So that's negative 11 plus 2 would give me a negative 9 lambda. And then it looks like I have a 6 here that will cancel with a negative 6 there. And I think that pretty much covers everything. So remember, we take that determinant, we set it equal to 0. This is not too terrible to factor here. I can factor out a negative lambda, and then that gives me a positive lambda squared minus 6 lambda plus 9. And I believe that that gives us the perfect square trinomial if we factor this lambda minus 3 times lambda minus 3. So here, if I solve for that first greatest common factor that I pulled out there, I would get lambda equals 0. And since from this factoring I get lambda minus 3 squared, it looks like we're going to have 3 and 3. Now, basically, what we're going to try and do with this is that, yes, I do have 2 eigenvalues that are the same. And a lot of times we just kind of ignore when we get the repeated root there. But I'm going to try and find linearly independent eigenvectors to go with each of those. Okay, so let's just start with what we know here. Lambda sub 1 is equal to 0. Let's just find an eigenvector for that. And if this is the case, then we're going to go ahead, plug in 0. We actually get back our initial A matrix here. And then we want to figure out what x1 would look like to set that equal to 0 there. So for this, really, you can do a little matrix operations if you want to simplify, but just know that you're doing as much as you decide you want to simplify here. If you just look at this first equation that's created with your system, you have 2 times x1 minus x2 minus x3 equal to 0. If you can find an x1, x2, x3 to fulfill this eigenvector here using just that, then that's great. You don't have to really do the row operations necessarily to solve this, especially because it's a long enough process already. So if you this is where I was saying yesterday, the guessing can kind of make us uncomfortable because it feels like we're just picking values, and we are. If I make x sub 1 equal to 1 here, then that gives me 2 minus the same values here. So if I just actually make each of those also equal to 1, that is an eigenvector that works there. I just have to make sure the others are also linearly independent from that. Okay. So that's my first eigenpair right there. It doesn't seem like I did a whole lot of solving work, but that's okay because that works. Now, we're saying lambda sub 2 and technically lambda sub 3 are both equal to 3. So what we're going to do is we're going to go ahead and do our A minus lambda identity matrix here. So I have to take 2 minus 3 on the main diagonal in each of those places. And if we're keeping score here, that means we're going to have -1 everywhere once we do that. So our goal is not only to find an x sub 2 eigenvector, we want to see if it's going to be possible to find an x sub 3 eigenvector as well. So I'm going to do a little simplification here because, well, I can't really add rows together or do anything like that. That's going to eliminate all of my elements, but I can make them at least all positive. And just looking at what I have here in terms of my equation, my system of equations are all going to be identical. So that's a little bit boring. But we will, if you augment this with your 0 right here to solve for x sub 2, again, what we're kind of seeing for our system is whatever I choose for x1, x2, and x3, if they add to 0, then we're good to go. So really, if I want to just kind of move things over and say, okay, x1 has to be equal to negative x2 minus x3, and then I pick some values that work for that. So, okay, let's say for my eigenvector, I pick 1 for both x sub 2, or actually, you know what? I'm just going to pick 1 for x sub 2, and I'm going to pick 0 for x sub 3, because then x sub 1 can be equal to 1. So just double checking here. Or I'm sorry, I guess this would have to be a negative, or you could flip flop those. So if I have -1 for x sub 1, it's equal to a negative x sub 2 minus 0. That works. All right. Another one here that works is, like I said, a little flip-flopping. So you could flip-flop your positive and your negative. You just don't want them to be linearly dependent. You want them to be linearly independent. So what I'm going to do instead is I'm going to just switch x2 and x3. -1, 0, 1, because then now -1 equals 0 minus 1. That works. Okay. These two eigenvectors are linearly independent, which is my goal all along, to make sure that they were. So now solving for y, we would have c sub 1 e to the lambda t, that first lambda was 0. And then that first eigenvector, we chose 1, 1, 1, based on what we saw from our matrix. Plus c sub 2 e to the lambda 2, which is 3t, times our eigenvector. And now we don't have to worry about a repeated root and treating it the same way that we did in the past because my eigenvector is different. So I'm going to do, but I do need to probably change this to c sub 3. So let's do that. C sub 3, keep it e to the 3t times the other eigenvector that we found here. Okay. Now again, we can put this into a more full matrix form here with our fundamental matrix, which would look like this. All right, times C, C1, C2, C3. My preference, and I think the book's preference, is that when you go to write out your general solution for y of t, is that you actually multiply those two matrices together. So we would have C1 minus C2 e to the 3t minus C3 e to the 3t. This works as our first solution to our system of differential equations. So we keep going. And of course, you don't have to write plus 0 there. If you see those coming up, like I'll see it coming up here with this last one. Nope. And I realized I actually messed up this element right here. This should be an e to the 3t. So I should have c sub 1 plus c sub 3 e to the 3t for that last solution there. Okay, so I'm just going to go ahead and get rid of my plus 0 here. And this would be my solution to my system of differential equations. Again, the general solution would take on this form right here. So I hope that was helpful. Let me know if you're having any questions with these before your quiz.